Hello again, folks. Today we're going to be covering section 6.5. This is a little bit faded, unfortunately. But anyhow, we're going to be doing section 6.5 and just 6.5. So, pulse to there. Today is, let's see. Today is Wednesday, February 10th. Alright, so we're right on schedule. If you're following along in the, at least in the assignments, you should be approximately up to section 6.5. If you're a little bit behind, you have time, of course, you have at least until March 1st. But don't wait too long, as I keep telling you, because it does get ahead of you. And it is involved. It requires, sitting for a long time. Anyhow, the packet that I have for you today consists of these pages. Right? First, there's a diagram that translates the model A is less than B, all right, from the symbols into what it would be in English, at least. All right. I stole this from the textbook, okay? Naturally. This is a diagram which you don't really need. Well, I made this. I feel that this, I will fill in a little bit here too. I made this a while ago for a different class, and I use it often to explain what the labels actually mean: rational, irrational, imaginary, and so forth. What is relevant to us really is what I refer to as integers, right? Negative and positive numbers, practically also zero. This is a diagram for when you're drawing in one dimension, graphing in one dimension. Let's see. And then there is a word problem that we'll go over. Okay? So if you're following along, try to print those, and we'll get started. Let me maybe turn on my projector for a moment. I'll do that in a bit. Is it too bright? It always depends on the time of day. So I don't know if this is better or worse. I really do need to get another lamp because I'm not casting a shadow. So let me turn the kitchen light on. Help a bit. Alright, a wee bit better with the light. Alright, all three. So good. It's as close as I'm gonna get, I guess. Eyeballs, where are you? There they are. Okay. Alright, section 6.5 is about inequalities. Alright, let me draw you an overview. There are different amounts of solutions in math. I'm going to abbreviate solutions, kind of the way my chemistry professors used to abbreviate the word solution. Now, they were referring to a liquid, of course, but a solution as in mathematics. There's basically two cases to look out for. There are, in the instance of equations, a finite number of solutions. It may be one, it may be two, it may be three, but it's going to be definitely finite. It's not an unlimited amount of them. All right? On the other hand, the subject for today, in the case of what are referred to as inequalities, there are infinite solutions. And that might make them seem pointless. All right. But there are infinite solutions usually bounded between two particular places, or they start somewhere, a reference point, and they head off into infinity in one direction or another. All right. Which is why, although we have the techniques that we employ, and I'm just using this as a vague sort of a model, we have an expression equals an expression, right? In the case of equations, this is the symbol that separates the two sides. That is why, even though we're going to basically use all of the same techniques, when you have an inequality, you're just using a less than symbol, all right, a greater than symbol, a greater than, pardon me, a less than or equal to, or a greater than or equal to. One of these to separate sides of an inequality. We can do something else that is maybe more meaningful, right? Very often the solutions for inequalities are, shall we say, illustrated. Rather than simply done or represented using these symbols, right? You take the work that you have evolved, right, developed, and you draw it on a number line, because as they say, a picture is worth 1,000 words, right? So rather than have to be even quasi-verbal, all right, you could draw a picture that means the same thing. That's all that this is. If you've have any inkling about what I'm talking about, if you've ever seen a number line and then there's a point on it and then an arrow headed off in one way or another, that is the drawing that represents the solution, rather than using these symbols, right? It means the same thing. It's an alternative. All right, anyhow, this is the subject of today. This is section 6.5. There's two things that you need to be aware of. So I'm going to erase this half of my little diagram here. When you are dealing with inequalities, there's two things to be aware of. Right, and that is that the orientation of the expression, and I'm just putting expression exp, and the inequality symbol, which is one of these four: less than, greater than, less than or equal, greater or equal, which again, if you need to, is the translation in this table here. Less than or equal to, greater than or equal to. Beware that the orientation of the expression and the inequality symbol is very important. You can get basically the same answer, but you'd have to say it verbally in a different way based upon the orientation. So for example, if you had something like x is greater than 3, if the letter is in front and then this inequality symbol is in the middle naturally, and then the expression 3 is on the right side, you're framing how you talk about it, in English at least, all right, from the perspective of x. X is what? X is something in relation to the 3. X is something bigger than the 3. If you got basically the exact same answer, if you wrote this 3 is less than x, it's saying the exact same thing, but it's using different words to convey it, right? And that drives people crazy, understandably so, right? But understand that this is now spoken about from the perspective of the 3. So you would say 3 is something in relation to x. It's smaller, right? That isn't untrue because x is bigger apparently, but you're talking about it from a different perspective. It's like standing here and talking versus standing here and talking. Right? The bait analogy that I always tell people, but I think it's memorable, is that it's sort of like talking about the same thing using different words. You could say that your roommate or whatever, I'm not going out, and that means something, right? But what is it implying at the same time without saying those words? It means that if you're not going out, you must be logically staying in, right? But not saying those words. So it is with these two situations. You are saying the same thing, really, but you're using different words. So the orientation of these symbols is very important. Right? What you want to do strategically try to write it like this. Write it in this arrangement. In the arrangement, letter, symbol, the inequality symbol, one of these four, and then the number. All right, and the reason that you would want to do that, put the letter on the left and the number on the right, is that if you are going to graph it, it'll kind of give you a little cheat. All right, it will tell you the direction of the arrow even if you don't translate it verbally that well, right? So if you can, try to strategically arrange whatever you get as an answer after you do your work. And I'll show you some examples naturally. Letter, symbol, number, right? Meaning you'd like this situation, right? Not this so much, even though it is technically the same thing, right? The other caveat is when you multiply or divide by a negative. Let's see if this is up to snuff here. When you multiply or divide by a negative coefficient. Remember, coefficient is the fancy way of saying numbers sitting in front of letter. They're attached, right? There's no plus or minus in between them. They're pressed together. It's a coefficient. When you multiply or divide by a coefficient, negative coefficient, there's a correction that we have to make. It isn't your fault or mine or anyone's. It's just something that you do logically because it would make the answer correct. There is a correction. Right. And shall I say, a necessary correction. Right. You have to flip the inequality symbol. Right. So in other words, if you start with something oriented as, and this is just a symbol, mind you, not the two parts, the expressions adjacent to it. If you have a less than inequality symbol, if this situation arises where you have a negative coefficient, what you have to do is a correction in the logic, in the algorithm of your work, is reverse it, basically. So flip it, reverse it, whatever you want to say. All right, if you don't do that, and I'll give you an example of it when it occurs, your answer will be false, even though your arithmetic is flawless, even though your algebra is beautiful, and you did everything seemingly right. you get a dud for an answer if you don't fix this, right? They're all problems. I don't think you're going to see too many of them in this semester, but let's say you took an Algebra 2 class where this flipping of the symbol occurs multiple times in the same problem, right? Perhaps for different reasons. All right. So let me go through this. Let me explain my little diagram that I made here, because it makes me happy. But I hope it's helpful too. I mean, that's really ultimately the reason I share it. I like to make diagrams. I genuinely do. Oh, I never remember to plug it in. For crying out loud, we're used to this. Hopefully it's plug and play and it won't implode if I do this. Let me just scoot this over just a wee bit. That seems to be okay. And I'll erase the superimposed nonsense here. That isn't nonsense, I just wrote it. It's floats, if you wish. Okay. Think of this as being, there are many diagrams to explain the sort of the nomenclature and labeling in math. And when I was a kid, although I liked my teachers very much, I don't remember anybody ever taking the time to do this, and I really wish they had. Right. So let me set a good example here. All right. Think of this as being something like a numbers family tree. You know, if you go to what is that, ancestry.com, right? They'll link you up to people you are distant cousins with. All right. Anyhow, the first dichotomy, the two labels that you have to choose from are that you have either real numbers, which sounds silly without this added information to include. All right, and its opposite essentially, which would be the opposite of real, imaginary. All right, this is, you probably don't even have to worry about this semester at all, but just for the sake of contrast, right? You probably your whole life, your math life, the best life, right? Up to this point, have heard in the instructions somewhere, hey, find all real answers, right? Well, what does that mean? All right. I'm just using the same numbers and whatever else that anybody else is using. So what do you mean real, right? This whole half of this diagram is what is considered real. There is basically this example of what makes something imaginary, right? But it's not part of this, so we separate it and put it in its own category here. The square root of a negative, right? If you have any familiarity with square roots, you know that it's kind of an amped up version of division, right? Normally when you divide something like 4, right, you draw a box like this. At least in the United States, there is a tendency to draw a box in this orientation, right? I have seen it elsewhere, and there's nothing wrong with that, maybe drawing it like so, right? I'm just sticking with what is basically familiar to me. There's normally a number written here and a number written here when you divide. Right? And it could be any two numbers, right? I'm going to cheat and just go, well, what if I was dividing 4 by 1, right? That would be a divisor, this would be a quotient, and it would coincidentally be the same number here. Yes, there is another type of division that is involving whole numbers, in which case you'd be dividing by 2, when you get coincidentally the quotient is the same number here. But when you have a square root, what you're asked is what number divided by itself would make the number here under this radical symbol is what it's called. And they have to be identical is the key phrase there, identical. It would be this scenario, right? This times this would make the number 4, right? And rather than put a number here or here, they just simply write it once, and go, well, it's 2. The square root of 4 is 2, right? If you are aware of the concept of negatives and positives, though, right, the question is a little bit deeper than just simply the numeral digit here. They have to be identical, so in theory, it could also be negative 2 times negative 2. That makes positive 4, right? Which is why, to summarize, a lot of times they will put a negative stacked on top of a positive, meaning positive 2 times positive 2 is one combination that makes positive 4, as well as negative 2 times negative 2 makes positive 4, right? From the rules of integers for multiplication, right? Anyhow, that's the abbreviation they would often write if they don't write this. Right. What happens though when you have a negative underneath the radical? Right? You can't answer the question is the problem, right? 1 times 1 would be the pair of like factors that makes this number. 1 times 1 makes 1. But when it comes to the sign though, you can't answer the question because they wouldn't be identical. 1 would be a positive in theory and 1 would be a negative, right? So you're not really responsible for this, but if you're trying to separate out in your brain, you know, real, what do you mean real? I mean everything that isn't this case, right? This is imaginary because we have it, for all intents and purposes, in our mind, right? The concept exists in our mind, so it's imaginary for right now, right? There are ways around this, right? We usually just designate this as an I, and then put a regular 1 in here, and then say, well, this by itself is just 1, so it's just I. 1 times I is I. We use I to represent this concept, right? It's not useful in ordinary arithmetic, right? But it exists in our minds. It's imaginary, right? You can't answer the question, right? But we're not going to throw it away. Okay. What is relevant to us really are the integers today, right? They're under a category of what would be defined as rational numbers, right? Now, 2 things. An integer is basically a whole number, all right? Which means it is not a decimal per se, right? And it isn't a fraction. You could take a whole number like 7, all right, and disguise it to look like a fraction, and that is why it is under the heading of rational. Because what does it mean to be rational? It means it can be a fraction. All right? Whereas what is irrational can't be a fraction. All right? Anyhow, the integers are an ultra-specific word in English. Right? And I'm only mentioning it because, all right, there's a problem you'll see that it's kind of a trick question, and they say, here, graph the integer solutions of this inequality. Well, what they mean by that is 2 things. That it's a whole number and it has a sign, right? So the integers are technically the negatives that are whole, 0, which separates all of them, all right? And then the positives that are whole, all right? So make that distinction in your mind, all right? When you see this phrase integer, they mean that it could be -7, -2, -4, 0, +9, +25, something that is whole, no decimals, no fractions, and there's a sign involved, with the exception being 0. All right. Now let's do an example, and I'll turn this off. Come on, go away. There you go. And let that be light here. As I alluded to, the the procedures for going through solving an inequality are thankfully the same as what have been established already. Opposite operations and whatever simplifying techniques you need to employ. So that's good news, right? If you had to solve this inequality, we'll do that just to get our feet wet here. 4 times the quantity 2x minus 1 is greater than 7x plus 1. All right. Remember, the ideal scenario for something as complicated and ugly as this is that we have the situation where we have letter plus or minus number, a symbol, it's usually equals, and then maybe the same thing on the opposite side. So more ideally it's just number, but it could be plus or minus letter, too, right? Also, right? And what we have here is that's pretty much what we have here, things that are at least boiled down to being not like. So you can't really add them, as the best that you can do is just simply park them next to each other. That's why it's 7x plus 1 and not something else. They can't be merged. Right? On the opposite side here, and again, we're just swapping out, instead of using equals, we're using greater than. We have 4 times the quantity, 2x minus 1. When you see something grouped as such, that's how you would say it in English. You'd say the quantity and then read the contents of the parentheses. Right? This is not quite the ideal here. Right? So if you put the blinders on and you look inside the parentheses, you might go, all right, well, maybe I could try to clean up the inside guts here. And that's good that you should check. But what you'll see is that, no, they're not like terms either, so I can't merge them. What can I do? The best that I can do is get rid of these parentheses by employing the distributive property, right? Which is basically just to multiply the outside by each of the contents on the inside. Right? And the result is 4 times 2x is 8x. And 4 times 1 is minus 4. And there's the symbol here still, and there's all this stuff. 7x plus 1. All right? At least we've gotten it down to this situation. All right? Now we can employ algebra. All right? This is basic arithmetic. Just multiplying. All right, next thing is, all right, and this is where I digress from perhaps the way you might have been taught it stylistically. I always draw a table, all right, and I'll stick with that because it serves me well. All right, I want to get the situation where it's just exclusively letters, as I said, strategically so, on the left side. They don't have to be there, legally speaking. But when you're trying to graph later, it would be to your advantage to have it oriented as letter on the left. So I'm going to take this 7x and try to drag it over here where its buddy is, right? Because they like terms. What is the sign of this if it's not written? What would you assume it is, right? Math people, unfortunately, leave out positives and decimal points and ones and zeros when it's a convenience. Right, so this is understood as being a positive to start with. If you want to justify moving a term, an entire chunk from one side of a symbol to another, you do the opposite operation, which means you take 7 and its letter. Right? A lot of times people mistakenly will take just the digit. No, take the whole kit and caboodle, right? The whole term. And then strategically plop it under here where it belongs, right? Where it's similar. All right. The effect of doing that over here is that there is a cancellation, right? I don't know what x is yet. I'm trying to solve for x, but you don't need to know what it is right now. What you need to convince yourself is that anything minus itself is going to be 0, right? So I'm simplifying in an algebraic way, if you will. All right, so I'm going to leave the void here and maintain this symbol as oriented as such, greater than. 8 minus 7 is 1. You don't have to write that. You can just simply write it in a more concise way, which is to say x. And then just because I'm running out of space here, I could bring down the 4, bring down the 1, draw another table, but I'm going to just do this in a different color. All right. If I have made the executive decision, if you will, to bring letters exclusively over to the left, and what I need to do is to bring regular ordinary numbers over to the right, right? And I do so again by opposite operations. Whenever you go over a symbol, you're doing algebra. What is the opposite of minus 4? Plus 4. And if I add 4 here, I must add 4 here. This is the balancing act that is algebraic technique. So there is again a cancellation effect. By design, these cancel. I'm going to leave the void for right now. And I'm going to actually combine these constants. All right, they're like terms. They're both regular numbers. 1 plus 4 is 5. All right. Now, since there's nothing else to do, I'm going to write them a little bit closer. And I have this as the end result. X is greater than 5. All right. You see that the procedures are basically the same. We're just opting for a different symbol rather than the traditional equals at this point. Thankfully, right? Now, there's a lot to say about this. I'm going to raise the gobbledygook here and talk about it. All right, now I'm going to write this here, just not to bend down, because it's killing me. I run 2 miles, at least like once every week or two, and I'm out of breath right now, just hunching here. So I think it's because it's squashing my diaphragm, right? And strangling myself, which is completely all my own fault, right? Nobody said, hey, Ziegler, you better get in that monkey costume, and get in there, math clown, and dress up. Nobody told me that. I just sort of took it upon myself. So I am to blame, all right? Anyhow, moving on. Let's focus on the situation here. We have established that x is greater than 5 according to that orientation of the symbol. I'm going to write that out in English now. All right, literally, what is this saying? All right, this means x is a number. I'm going to be a little bit more plain spoken. Bigger. What is this? I don't know that number. Go away. All right, number greater than, bigger than, same difference, than 5. It's probably asking me to extend my 20-year-old car warranty, all right, which makes no sense. All right, anyhow, x is a number that is, really should say greater, but you know what I mean, bigger than 5, all right? So think about that for a moment, all right? What is that implying? Right? When you imply something, you're not really plainly saying it. You're merely alluding to it. Right? You're suggesting it in a subtle, vague way. Right? Not really saying it explicitly. Right? You are saying, well, x is not 5. That's weird, right? Because normally when you solve equations, right, especially if you go through all the trouble of the work, right, what do you establish? You get, well, all right, this letter is that number, right? Specifically, this letter x is equal to 5. If you had this situation, x equals 5, it is telling you explicitly x is 5 and nothing else, Right? In the case of inequalities, though, it's infinity. Pardon me a minute. I shouldn't even be answering my phone. What is this? Why would I want to? That's very strange. I have a feeling that's a Toyota dealership. And I don't own a Toyota. I wish I did. Right? Anyhow, X is 5, right? Remember the equal sign translates to is in English at least. Right? And, or whatever the equivalent would be in another language. But when you have an inequality, it weirdly tells you what it isn't. Right? That's bizarre, right? To go, X is not 5? Yeah. But what isn't 5? Infinity. There's a ton of things that are, that's the bottom line really, that are not 5. And if you were saying it's something bigger than 5, that is suggesting X is something beyond 5. Beyond 5 in a specific direction. Right? And that direction in this case, in this unique example, is that way. That is why I suggest to you, strategically rig your answer so that you're reading it from the perspective of the variable, letter on the left, because if you do that, it tells you the direction of the actual solutions. It's not 5 because there's no equals in here, but it is something beyond 5 in a specific direction. That way is where the answers are, if you will. I'm gonna get some water. Let me draw you another diagram. Okay, I'm going to use this as an example a lot, right? Since we took the time to solve for it. Now, there's different ways to present the answer. That's one of them. Right. Let's do a diagram here to summarize. Let's call this solution presentation. In other words, different ways to write the answer. There is the traditional way, which you've seen, right? Which is using, hopefully this is a good marker, traditional math symbols. It's got too much flair. And then there is this way, which is not, you can do this when you have it in a regular equation as well, but people tend not to bother. When it comes to inequalities, they opt for this very often. Instead of using traditional math symbols like we had, even with an inequality symbol, what you might do is using a drawing. Now the drawing usually has two options. It usually has, and I'm going to put the an abbreviation W here, and then a forward slash. All right, it means with. All right, and then you put the thing afterwards. With traditional dot on a line, or I'm going to put this symbol and a hole. With a traditional dot or a hole. All right. On a number line. Slip in here. Okay. Again, you have the option, even if you are using equations, right? You could do something similar, but when you were discussing the solutions of an inequality, there is a tendency to do this instead, a drawing, because again, you know, the old adage, at least in English, is a picture is worth 1,000 words. In other words, it summarizes anything that you could say verbally, right? And there's a grain of truth in that, right? That if you try and explain something to another person, you can talk about it, right? But sometimes it's more clear, hopefully, all right, when you draw a simple picture that summarizes anything that you could say, right? It's more internalized, for lack of a better phrase. You see, even now I'm stumbling over my words. All right, anyhow, we're going to do a lot of drawings using a traditional dot or hole. The reason that I say traditional is because there are amped up, modernized versions of these illustrations. All right, you're not responsible for them. I'm just going to tell you what they are, in case you come across them. Another way to draw, and here's a little thought cloud, is that you use with interval symbols. All right, so a lot of times what happens is that instead of a dot on a line, what you will see is a bracket. All right, and instead of, this is what a dot would relate to. When you see instead of a hole on a number line, what you would see is a parentheses. That translates to what you have as a hole, all right? The bracket can be oriented this way. The bracket can be oriented that way. It depends on the inequality. And similarly, the parentheses, all right? Anyhow, if you think of a hole as being two parentheses mashed together, that kind of makes sense, right? Anyhow, these are called interval symbols. And then a simplified version of that for, you know, upper level math is that they would write something in interval notation. Interval notation is something that might look like a coordinate. There's a number and then a second number. That basically summarizes the drawing. If the drawing is a summary of the work that you've done, the interval symbols can be then even slimmed down to their bare essentials so that you have something that kind of looks like a coordinate, an ordered pair. It isn't really, because it's not two-dimensional, it's one-dimensional, but it simulates that. It represents an interval, a spectrum of solutions, right? A spectrum of solutions. And then, of course, there's yet another one, which you might come across this eventually, which is called set builder notation. Set builder notation is the fanciest way of presenting the answer. It doesn't change what you're actually talking about. It's just like as if you took it and you mounted it to a plaque and you went, behold the wonder, oh, inner light comes out of it because it's so beautiful, right? That's when you see things like these fancy braces. and then an inequality, and then a closed fancy brace. Fancy braces is set builder notation. A bracket in some combination with a parentheses, perhaps, that is interval notation. Just using the intervals on a number line, you can get away with doing that, but then there's the actual dot in the hole. We're responsible for this right now. Okay? This line, incidentally, between the X and the conditions here is, in English, it's read as such that. And now it's very, very fancy. All right, let me do some examples. The traditional math symbols, using the example from before, would just be this. X is greater than 5. All right? And again, we want to strategically write it letter, symbol, number, if we can help it. And you always can, really. You just got to take the time. What I'm going to do now is draw a picture to summarize that information. So let me erase this. And we'll zero in on this now. All right. If I have concluded this, X is greater than 5, when you draw a number line, keep it simple. Right? Less is more. You've heard that expression? Right? This is, I don't know if this is an Americanism or it just maybe a British colloquialism. It's an old adage, an old saying, right? Less is more, old now. Meaning that if you put too much information in the drawing, it's confusing and it defeats its purpose. So when you're drawing a number line, I would include just a couple of things, right? Draw a horizontal line It doesn't technically have to be horizontal, but it usually is, right? 0, because if you're aware of the concept of negatives and positives, 0 separates out negative from positive, right? So we're always going to use 0 because it does that for us. And the number in the problem, the number discussed. You know, so like in our case, the number 5. If you purposely put the 0 in the middle of your number line, it would help you draw the picture, because then you could just simply plop that number in relation to the 0. It's a reference point. Where appropriately would 5, and this is a positive 5, where would 5 go in relation to 0, right? Since the positives are always on the right side of 0, you could put one little increment here and then label it 5, and that is it. You don't have to include 3, 4, 2, 1, or whatever else, all right? Think about it this way, and it isn't wrong if you did this, but when you were a kid and you had a graph, maybe the first time that you had graphed in one dimension is what you would call it technically. If you ever did this the first time, your teacher might have said, hey, label it, right? And so you would go 1, 2, 3, 4, 5, 6, 7, 8. And because numbers are infinite, you don't know when to stop, right? So again, less is more, right? It isn't wrong if you put those increments there, but they are unnecessary if you include 0, because 0 is telling you this is the middle,
It's the reference. And anything that we're talking about unique to the problem can be oriented in relation to that. So you don't have to do this, right? And thank God for that, right? Thank the universe, all right? Because imagine you had 57, right? You really want to do that? You can, right? You're gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, go all the way up to 57, and by then you're gonna lose count, right? Anybody would, all right? Unless you're like getting out the jeweler's loop and you're going, right? And you're really laboring over it. Then we're like, oh yeah, it has to be perfect, right? All right, don't do that. Don't torture yourself, and don't make me do that either. I hate that. All right, less is more. All right, so to help you, all right, one thing I did was I drew a diagram, and you can print it and as many times as you like. All right, so let me just show you that, because I'm kind of proud of it. All right, humor me. And let me turn this off. Turn that back on, rather. Let me open this up. Here's the diagram again. You don't have to print this, but I made it for you. And I want to discuss it a little bit. And we'll use it to graph this, at least this one time. Get rid of all the distraction here. I'm going to put back just two things that I've erased here for a moment, and then I'll continue. All right, here's the problem at hand. X is greater than 5, and these are the symbols that we can use. We can either use a dot, or we can use a hole on a number line. All right, what do they represent? A dot means included. All right, and a hole means not included. Batteries not included. Okay. All right, if you have some kind of equals, some form of an equals, then you would appropriately use a dot. If you have just a greater than or just a less than, then you're using a hole exclusively. Okay? Now, we're doing graphing in one dimension. Right? And we'll be doing that for inequalities. That's usually what you do. In inequalities, it's graphing in one dimension. Right? In theory, you could graph with inequalities in in 2 dimensions at the minimum. All right, and probably a third. I never have. All right, it is possible. All right, just I don't remember. I don't remember doing that even in calculus, to be honest. But I mean, it would be in theory possible. Anyhow, graphing in one dimension is one line. Right. Numbers are infinite, right? So rather than, as I'm trying to, impress upon you, comedically putting an increment for every whole number, right, into infinity, which is a futile task. What you could do is just draw a horizontal line. It can technically be vertical, but it usually is horizontal, meaning this orientation, and it's usually labeled X, all right? And then maybe label where it's pointing to, right? If, as I said, from 0 beyond this in this direction is infinity, it's positive all this way. And from 0 back here into infinity is negative infinity. The sort of sideways 8 symbol is the infinity symbol, which means that it goes beyond wherever you cease to label. Anyhow, less is more. You don't have to put the increments exactly, right? Just draw a line like so. Maybe label infinity wherever it's headed, all right? Include 0 and the number that is relevant. So if we're talking about 5, you put a 5 appropriately in relation to 0. If I happen to have graph paper, the increments are already there. So if I want to be really precise, I can count 1, 2, 3, 4, 5, and just put one obvious increment here and label it 5. You don't have to label 4, 3, 2, 1, or whatever. Now, in our problem, this one, the way that it worked out was that it was x is greater than 5. Now you could reason with yourself and go, all right, well, what direction are the things that are greater than 5? Ultimately, it's towards the right. But if you feel sketchy about it, pun intended, because it's a drawing, right? Just remember that if you strategically orient your answer as letter, symbol, and then the number, you can sort of verify that your intuition was correct, because the point of the inequality is pointing in the direction that the rest of the answers are. So, question. Before I go off in that direction, should I use a dot here or should I use a hole here? And the answer is you should use a hole, because even if it looks like little crosshairs, right? I'm assassinating poor number 5 here. Appropriate that's in red, right? Bad joke. All right. 0 in, right? It's appropriate to not use a dot, but just simply a hole, because remember, 5 is not included. The weird thing about it is that even though we took the time to solve this, we have established that it isn't 5 is the answer. It's just merely a reference point. It's merely where you start looking for the answers. Where are the solutions? That way. Now, how do you do that? Illustrate that? Traditionally, you scribble, right? People tend to do this. In that direction. Make an arrow that is obvious. And that is sufficient, right? Remember what is being established by an inequality. It isn't just one answer. It's not finite. Inequalities express a, for lack of a better phrase, a spectrum of solutions, right? It's 5 and it's not 5, it's 6, right? And it is 7 and it is 800 million. And it's everything in between them, right? So even 5.1 is in fact an answer. It would be immediately after 5, right? 6.28971, some decimal, right? Is part of the spectrum of infinity in that particular direction. So even if it seems kind of silly, like, all right, well, what have I done? I've established that the answer isn't 5. You've established where you start the rainbow, right? Fun. Yay, rainbow, right? All right, it is nice. All right, but like, I always think of this song from SpongeBob, right? You know, when he's trying to shiver plankton. He sings fun, right? Fun is for friends who do stuff together. U is for ukulele. And then plankton, you know, sort of makes it horrible. U is for uranium bombs. Well, this is a spectrum, right? A rainbow, if you will, of solutions that start here, right there, and go into infinity this way, right? Do you have to do this on graph paper? No, I only made it for you because eventually we're going to get to 2 dimensions. And on 2 dimensions, you really do need to use graph paper. Anyhow, when you're just drawing it freehand, same thing. Use a hole, because it's not included, and then draw an arrow in the direction where the answers should lie. All right? If you want to put it parallel to the actual number line, that's cool too. All right. Let me turn this off. Uh-oh. Thought I killed my computer for a minute there. Alright. Moving on. Let me turn the lights back on. I'll do another one more quickly. and then we'll sort of shift gears here. All right, suppose, as another example, you had to graph this. All right, x is less than or equal to -2. Right, graphed. Right. We're graphing again in 1D, which doesn't sound too impressive, right? Usually when you go to the movies, right, it's 3D, right? No, we're just sticking, Math World is just one-dimensional at this point in the conversation. So keep it simple, right? Draw a horizontal number line. Appropriately place 0 in the middle, just to get started, because again, it separates out the negatives from the positives. And if you want, label infinity. This heads off into positive infinity, and this heads off into negative infinity. All right, now, the relevant number in this particular problem is -2. So where in relation to 0 would you appropriately plop -2? On the left side of it. Do you have to put increments between there and there? No, just roughly just put -2, right? That's where it should go in relation to 0. That's the whole point of 0. It's a frame of reference, right? It's a reference point. So in this case, it is indeed an inequality because it has this less than symbol, but it is simultaneously equals. This is less than or equal to. Again, here's this page, this diagram here. All right, if you need it, here's these references. All right, these are using A's and B's, of course, as a model, and these are, in some instances, greater or less. All right, but it is this situation that it's a less or greater, and then it may be or equal. All right, so if there's an equal here, and you had to choose between the dot, which means included, or the whole, which means not included, all right, which should you do? Which should you use in this case? You should opt for a dot. Opt for a dot. Because 2 is part of the spectrum in this particular example. All right, so you would proudly put a dot here. Now, again, it's a spectrum. It isn't just 2, -2. It's everything beyond it in one particular direction in this case. So, again, if you took the time to strategically orient it as letter, symbol, number, the less than symbol tells you the direction that your arrow should go. So I'm going to draw a parallel line, right, rather than scribble. I like parallel lines better. That's just my preference. Right? You could do it any way you like. All right? As long as it gets the point across. All right? Literally, it gets the point across. Right? So this is where the spectrum exists. It starts at -2 and it heads off into negative infinity towards the left. Okay. Let's do some examples. To illustrate the other pitfalls you may have to look out for. Here's a simple one-step inequality. All right, suppose you had to solve and graph it in one dimension. in 1D. Yippee-yahoo. Here is the problem. Negative 6x is less than 18. All right, it's a one step, so it's not too complicated, right? If you're going to solve for x, again, the procedures are identical to what you would if there was an equals here instead. So if we're going to solve for x, we got to get x alone, which means we have to move 6 from here to the opposite side. All right. What is the opposite of multiplying? Dividing by what number? Negative 6. And then if you did it here, you must do it here, negative 6. Now this is a situation where you have to make that correction, right? Make the correction. Which again, it's not your fault, it's just the way it is. All right, flip the inequality. Because this is a negative coefficient. So when you multiply or divide by a negative coefficient, in this case we're dividing, we have to flip the orientation of this to greater instead, right? The cancellation effect still works, right? 6 divided by 1 is still 1. 6 divided by 6 is 1. A positive divided by, a negative divided by a negative is a positive, right? And then you're left with x. But now it is x is greater than the outcome here. If this is a positive 18 and you're dividing by a negative, this is a negative overall 3. Right. That means that if you graphed it, again, less is more. You use a number line, you put a 0 to separate out negative infinity from positive infinity. And then you take the number that is relevant, to this particular problem. Negative 3, in relation to 0, where would you place it? On the left side, so you just put a single increment here, negative 3. And you ask yourself, is there an equals in this or not? There isn't an equals at all. So we're going to opt for a whole, and we're going to draw an arrow that way. The arrow is now pointing this way. So your graph should look something like this. Right. If you'd like, you could do a scribble instead. A lot of times that's what your teachers would encourage you to do. I don't like the scribble because it gets messy personally. And sometimes you have a compound inequality, as you'll see later, where there's a lot of scribbling. So this is fine, really, but I think the arrow that is running parallel gets the point across as well, and it's less messy. All right. Anyhow, watch what would happen when you check the answers, right? I'm going to do the work over here, all right? If you didn't make that correction, you're going to get a bogus answer. Right? So I need a little bit of space. I'm going to put this here. If I do the check, right? After correction is made. And then immediately under that, I'll do the check again, right, without the correction. Right, you'll see that you're going to get a dud for an answer. All right, now, this is correct. X has to be a number that is greater than negative 3. Remember, when you're dealing with negatives, the things that are magnitude-wise that are smaller, like negative 2, are closer to the positives. They're closer to 0. So what is the next whole number that is an integer, whole number, that is greater than negative 3? Remember, you're heading in this direction. All right? The next whole number is negative 2. It's closer to 0. It's considered greater than negative 3. This is true. All right? Negative 2 is indeed greater than negative 3. All right? So I'm going to use negative 2 in my check. which means that if this is the original problem, -6, and I'm going to substitute with as an x, less than or than 18, and I'm going to insert 2, -2. I'm using the original problem. What do you get as an answer when you multiply? When I substitute -2 in place of x and I multiply these, negative times a negative is a positive, and 6 times 2 is 12. Is this true? Is 12 less than 18? It is, right? We made the correction and it gave us something that works, right? So this is cool, right? Let's see what would happen if I didn't make the correction. Without the correction, the answer would have been x is less than -3. And the number line would look like this. A hole and then an arrow this way. What numbers are less than -3? The first one, and you should go with the first one just because it's usually easiest, right, is -4, right? A little bit further away from the positives, further away from 0, even though the magnitude is larger, we would say -4 is less than -3. That is true, right? Because it's further away from the positives, right? Anyhow, if I use this in my check, -4, see what you get. -6, I'm going to put a parentheses around x just as a little pocket that I substitute into. I would insert -4 in here because that's what the instruction would suggest I use, right? A negative times a negative is indeed a positive, right? But what is 6 times 4? 24, right? And this is the way it was originally oriented, these inequality symbols, so it's less than, and this is what's on the opposite side, 18. Is that true? Is 24 ever less than? It's not, they're both positives here. Is 24 legitimately less than 18? No, this is false, right? That is false, right? Which means that is not correct, right? We have to make this correction, right? Whenever you multiply or divide by a negative coefficient, right, you have to flip the inequality in this orientation. You could say reverse if you like. Right? Otherwise, you're going to get a dud for an answer. All right. Let me show you a weird case I was talking about or alluding to. There's a question like this. It says, solve and graph, all right, x minus 1 is less than 3, where, because it's a place, x is an integer. What this is implying, when they specify this condition of integer, is that the answer is not as, this is implying not a spectrum, right? But it is discrete points instead. This is kind of unusual, and that's why it was worth mentioning, I thought. Let me go through the trouble of solving this. I'm going to, again, draw a little table like I always do, and make a little line of scrimmage here to separate out left and right, and recognize that in order to isolate x, I have to move -1 from here to here, right, which again I will do via opposite operations. So I'm going to add 1. Add 1, there's a cancellation effect, x is left over. This is still oriented as less than. And then we're going to add these, which would be 4. All right. Now, under normal circumstances, you would then draw a number line. All right, and again, keep it simple. You put a 0. That is a funny line, sorry. It's a little bit straighter, I hope. Put a 0 to separate out positive from negative. This is headed towards positive infinity. This is headed towards negative infinity. And the relevant number here is positive 4. So in relation to 0, I'm going to plop positive 4, 1 increment right here. You don't even have to put the positive sign if you don't want to. Right? First of all, under normal circumstances, all right, there's no equals in this, so I'd have to put a hole here. Right? And then, again, if I was careful, right, I would have to draw an arrow coming off of it in the direction headed towards the left because it's something less than 4. Well, what's less than 4? Things this way. So I would draw a picture like this. Or I would do, again, the scribble. Right? In this instance, the scribble will help me, so I'm going to just go with that. Right? Because there's an extra caveat here, a little condition, which says, graph this where x is an integer. Right? Remember, integers are what? Positive or negative or 0 wholes, whole numbers. Right? Meaning not decimals, which means that what that is implying is that this is no longer a spectrum. Right? It's not a continuous scribble. Right? There's going to be gaps in it, unfortunately, because we're only going for the discrete points. That is just the whole numbers are going to be relevant. So that means the picture needs to be modified, right? Instead, you would have a drawing like this. This is one of the rare instances where it might be to your advantage to, when you're incrementing it, do more than you would, right? So here's 4, and here's 0, and now I would take the time in this particular weird problem, increment positive 3, increment positive 2, increment positive 1, negative 1, negative 2, negative 3. You don't have to do all of them, but you know, to get the point across. All right, and then instead of, because it can't be a spectrum, don't do a scribble. Right? There's got to be gaps in it. Right? It has to be if they're discrete points and it's just the whole numbers. So what are you going to do? You're not going to put a hole here because it isn't even necessary. Right? What you would do is you would put a dot at 3. You'd put a dot at 2. You'd put a dot at 1. You'd put a dot at 0, at negative 1, at negative 2, at negative 3, at negative 4 in this general direction. They have to be discrete points. Right? If they're integers. Okay? And I'm just going to leave 4 here because it's not included. There's no equals in this. If there was an equals, then I would include that as I put a dot there. But it's just a reference point. It's where you more or less begin looking when you're headed this way. Okay? All right. Let's shift gears here. Tenacious green. There is this concept, and it requires another diagram sort of to abbreviate myself. There is such a thing as a compound inequality, which basically means 2 at the same time. Right. What I would do, if you're writing this, fold your paper in half, right? So that you have something like this. Y'all. My sister moved to town, I see or something. Alright, anyhow. Fold over a paper like this, because what I want to give you is something that is, you know, compartmentalized, right? The information that is one of these two examples here, and then the other type here, all right? That is if you want to write this. All right. Of compound inequalities, and again, it's like two at once, two at the same time. There are the and type of inequalities. You'll see the word in English and. And then there are the or type. Or. Not to be confused with a rock. All right. A rock, an or rock. You know, like iron ore. There's those phrases you'll see, which you'll be able to identify which situation. And I'm going to try to separate these two. And then there's the more technical jargon way of referring to them. All right, these are called conjunctive. Right. And these are called disjunctive. Right. What I want you to do is associate these two things with a peculiar mathematical symbol. Right? If you've ever seen this sort of horseshoe shape before, you might know what I mean. This is the symbol for intersection. Right? And then its opposite, well, for all intents and purposes, the other type, which is a little bit more intuitive, at least in English. It's union, right? Right? Union. Right? So if you see this symbol, or this condition has been expressed somehow, know that you're dealing with a conjunctive type of compound inequality, or we can just say it's the and type, all right? If you are told, look for the union, right, it's the disjunctive type of compound inequality, or we can just call it the or type. All right, now, when you have intersections, what you are concerned with primarily are where there is an overlap. All right, in the drawing. Okay, when you're concerned with a union, everything is possible. Anything, everything that is possible. It's okay. May I have the cell phone number? All right. All right. Now, there are models that I'm a little bit short on real estate here, space. So what I'm going to do, area, I'm going to erase a little bit above here. Still sticking with this as the heading. You could write it underneath it. All right. What this would look like. All right. Sure. I'll wait until you have it. That's okay. Yeah. I'll keep it with this color here. The model would look something like this. There's the all-seeing eye here. So pretty, look at it. I'm giving it mascara. Here we go. All right. Anyhow, I'm a weirdo, I know, but it just makes me happy. All right. X. All right, is a variable usually that we use, and there are inequality symbols. As I said, it's two at once. So you'll see a variable, and there might be an inequality around it, here and here. All right. So I'm going to just put A on one side and B on the other. All right. this particular type, the AND type, right, can be rewritten in a different way. And when you're doing the actual work, you probably would want that, right? Can be rewritten, can be alternatively written, separated, separately. So you would have an inequality here, and again, if I'm being strategic and I'm going to orient it with the variable, the actual variable is x, being on the far left, it would be x, all right? And then the inequality symbol, maybe I'll just stick with what I have here, green, all right? X, and then the inequality symbol. Now this is where it might get a little hairy. Where is the point facing? It's facing the letter A. So when I write it in the orientation with the X not in the middle anymore, but on the far left, I must be consistent, right? It would be oriented like that. The point is still facing the letter A, right? And then the word and then again, X, and we will proceed to do this pair, all right, here, all right. This one you don't have to tweak too much. It is already in the correct orientation. So you have the point facing the letter X as it was, all right, and then the letter B. Okay, so it can be given to you, the AND type, the conjunctive intersection type, can appear this way, or you could write it this way. These are interchangeable, right? And they're options, they're alternatives. When you have a disjunctive type, there is no option, right? They're always separate. The model would look like this. The model would be like so. A and B, right? You would see it that way and never any other way, right? These cannot be doubled up. Okay, so just be aware of that, right? When you have something that is given to you in this way, you can double these up. It can be doubled up, for lack of a better phrase, right? Like so. Right? Now, insofar as the graphs are concerned, let me give you that a little bit of information now. I'm going to erase this for a moment. Forgive me, because I need the space. Right. When graphing, these compound inequalities that are the AND type, right? Ideally, right? These should overlap. They should overlap, right? Right? And that overlap only, that is the spectrum of solutions. Only. That place where they overlap is the answers, basically, right? If they don't, if there is no overlap for this particular type, the AND type, the intersection conjunctive type of compound inequality, right, then there is no solution. Not uncommon anyhow. Okay, for this particular type. These, when you're graphing, they may or may not overlap.
You said you have caller ID on your
Right? You don't really care if they do or they don't. Whatever will be, que sera, sera. Whatever will be. Right? When you're the or type, right? They may or may not overlap. If they do, great, right? But if they do, if there is an overlap, there's a special answer. Then the answer is Great Gatsby R. Right? All right, it looks like the Great Gatsby font, right? That 1920s font, all right? All real solutions, all right, are possible, right? If this happens to overlap, usually it doesn't. Now let me give you some examples and then we'll do the word problem and we're done. Alright, we're going to graph this problem, which is going to be given to you as -3 is less than x compounded with less than or equal to 2, right? You might ask yourself, right, when you're graphing this, all right, which type am I dealing with? The AND type, red, right, or the blue type, or? It doesn't have to be those colors, but I think it's good to be consistent when you're teaching, right? Try to associate a color, and don't use green next to red if you can avoid it, because it's hard for people who are colorblind to see, right? So, it looks like 3D most of the time anyway, right? This is, I'm going to rewrite it as the X in front, right? The wide side and the point facing what it was. The point is still facing -3. And this type, X is oriented less than or equal to 2. You don't have to worry about that. Right. Remember, when you're graphing, keep it simple. Right. So we're going to do one number line. And we're always going to include 0. We may not need it, but we will always have it because it helps in a very subtle way separate out the positives from the negatives. All right? And we will appropriately place, right, -3 in relation to 0 and simultaneously 2 in relation to 0. So -3 would be appropriate over here, right? On the left, I should say. This is an example of where English gets you in trouble. Right is, I'm using it in the context of correctitude, all right? Correctness, all right? But that's because of superstition way back, right? Even Latin, the word for left is sinister, right? Dexter, sinister, all right? Anyhow, don't automatically assume right is correct. I mean, right as in this belongs on the left. English strikes again, right? So it gets you in trouble, math teacher. Right? 2. 2 would indeed be on the right side of 0, right? Because it's a positive 2, right? -3 would be on the left side of 0, correct? All right, good. All right, now, if I were graphing this independently, right? This does not have an equal sign in it. So if I had to choose between a dot and a hole, I would put a hole, right? And here's where I would avoid scribbling because it gets messy really easy. If you drew a parallel line above the line, kind of helps. So this, again, because I was very strategic, tells me that the arrow goes that way. So I'm going to have an arrow headed off in this direction into positive infinity, right? Simultaneously. For lack of a better, I'm going to use black now. This does have an equals in it. So if I had to decide between putting a hole here or a dot, it would be appropriate to put, in fact, a dot here, because that means that it is included, right? And again, if it is strategically letter, symbol, number, this tells me the arrow heads this way. So I'm going to now just draw alongside of it an arrow that runs like so, right? This is where it gets interesting, right? The graph has to be altered, all right, to really genuinely express the legitimate common spectrum of solutions. That is, that you're meeting this condition and that condition correctly, all right? We are concerned with an intersection when we have an AND statement. So therefore we only want the overlap that we want. This may, by itself, the 3 situation, go into infinity this way. This 2 situation by itself may go into negative infinity, right? But we only want the overlap for an AND intersection conjunctive type of problem. So, where do the solutions legitimately lie? Only where they overlap, right? You could put a scribble now if you want. The scribble would be from here to there, right? If you want to rewrite it in a slightly more aesthetically pleasing fashion, draw a hole, a line, and then a dot. Looks like a molecule, right? And then just label it -3 and +2, right? This is the spectrum of solutions, right? All right? They're bounded is what you would call them as a technicality, all right? You might say, well, doesn't the arrow go this way? Yes, but you have to meet most conditions simultaneously. So that hole for an AND type of problem is always going to be there, all right? This is filled in, all right, because it was an equals to begin with, right? So you have that. If you want, you could draw the rest of the arrow like that, in this way. But this is basically where the solutions lie, right? From here to there, right? You might say, all right, well, doesn't that make it finite? It cuts off infinity that way and this way, but think about the infinity that is in between, right? I'm just considering the whole numbers 3 and 2 here, right? -3 and +2. But there's 0.000009, right? That in theory exists in between these two. So there's infinity in one direction or the other, and then there's the infinity that is in between them. So it's still infinite number of solutions. It's still a spectrum, right? They're not discrete. Right, to illustrate. Okay. All right, here's a slightly more complicated problem. All right. We're going to solve and graph this. To start with, negative 4 is less than this complicated gobbledygook here. X plus 2, 3 rather, over 2. It's not that bad. I'm belly aching. All right, less than or equal to 5. All right. Now again, because as you can see, it is doubled up, for lack of a better phrase, right? This is another example of the AND type, right? Because it is doubled up. So identify it as such, which means that I can break it into that problem is the letter. I'm going to write it on the far left, x plus 3 over 2. I'm going to make sure that the orientation is genuinely preserved. It's just going to look different, right? The open end is facing the letter. So the open end must be in this orientation facing the letter. The point is facing negative 4. Right. And over here, I'm going to take these two and write them pretty much as you see them. X plus 3 over 2 is less than or equal to 5. And I'm going to write the word AND in between them. Because this is an AND type of problem. Okay? Now, it is more than one step, right? And the other example was already solved. So if it's 2 steps, all right, we'll go through it. All right? Because there is this 2 under here, all right, what I should do is move the 2 first. All right, because it happens to be under both of these things. What is the opposite of dividing by 2, as this implies? Multiplying by 2. If I did it here, I must do it here. All right? The effect is that these 2's cancel, because this is technically above a line and this is below a line. All right? What that leaves you with is this. All right? X plus 3 is greater than negative 4 times positive 2 is negative 8. And now I'll just simplify by continuing. I'm going to move 3 by subtraction. These cancel. X is going to be, I'll keep it consistently in red here. X is greater than, a negative and a negative is a bigger negative when you're adding or subtracting. So same signs, add them, you get a bigger negative. So this is 11, right? Save that. This is correct by itself, right? Over here, you're going to perform similar techniques. Again, because this happens to be grouped as such. Divide by 2, you really have to move the 2 first, right? So to justify moving 2, you do the opposite of dividing, which is multiplying. I'm going to use a dot, just not to confuse it with the variable x, right? And do it to both sides. There's a cancellation effect, right? Here, and then what are you left with? You're left with still the same x plus 3, less than or equal to, the outcome of 5 times 2 is 10, right? And you continue with this. Move the 3 via subtraction. Here and here, these cancel. What is left over? X is less than or equal to, this is a positive 10, and this is a negative 3. When you have one of each, you subtract, which means that you will establish a digit of 7. It will take the sign of the larger magnitude, which is basically the distance from 0. So 10 is a greater distance, so therefore this is a positive 7. Save that by itself. And now we're going to graph it. I need the space, so I'm going to put this up here. All right. So, number line. It's not really straight. Oh God, why is it? Just dreadful. There's arrows. Here's 0, and I'm going to put this on the line here. Negative 11 in relation to the 0 would be somewhere over here. It doesn't have to be perfect. All right. Positive 7 in relation to 0 would be somewhere over here. It doesn't have to be perfectly incremented. All right. In this case, we have a whole because it's less than. And if I took the time to strategically write the letter in front, the arrow should be that way. Coincidentally, similar to the last problem. And the x is less than positive 7, so the arrow should be this way, just as it's oriented. So this has an equal sign, so I'm going to put a dot here as well. Right? And there would be an arrow like that. Where are the solutions for an AND type of problem? Again, ideally, when you have an AND, you want an overlap. Right? They do in fact overlap. So a dumbed down version of this would be to delete out the arrow that runs this way and the arrow this way. Right? Or you could just put whole, line, dot, like a molecule. 7, negative 11. Right? That is the spectrum. Right? The number line goes this way and the number line goes this way, but we only care about the spectrum in between. They're bounded. Right? Basically. There's nonetheless an infinity between these numbers. If this was an OR type of problem, and it wasn't, right, then what would happen is that anything and everything is okay. So there wouldn't be a hole here in that instance, and you'd say, oh, it's all real numbers. Right. Interestingly, if you want, I wrote them as separate, you could put them together, right? And you would say there's an x in between here, and there's a negative 11 on the far left, and there's a positive 7 on the far right. And the orientation of this is less than or equal. And this one, notice where the point is facing, the 11. So you'd have to have a point still facing the 11. This is a doubled up version of this. Sometimes instead of the word and, they just use the horseshoe shape. Right? This, horseshoe, that. One more. Right, now, if you take a look at this word problem here, I'll go over this. I'm going to turn on my projector to do that. And kill the lights. So, all right. This is an example where you would translate this from English into mathematical symbols. There's a bit to it, but it's interesting. And it's applicable. Okay. I'm going to scoot this up just a little bit so that I have a space to write. And maybe just shrink this a wee bit. There we go. I don't know if you can see that, so let me go back. A student must have an average. An average is sometimes referred to as a mean, which is a formula. It's the sum of all the numbers divided by the number of numbers. All right? An average of 5 tests that is greater than or equal to, meaning you're going to use this symbol, 80. But also less than that symbol, 90. So this and this are going to be incorporated somehow, right? In order to receive, this should be here, a final grade of B, right? If their test scores were 98, 76, 86, and 92, what would be the range, the spectrum, of possible scores on a theoretical or hypothetical fifth test to qualify for a B. Right? What you have to sort of do here is ignore this bottom sort of paragraph here. It's really one sentence. Right? And just try to translate what you see here. I purposely tried to make certain things stick out, like I put this in bold here, and this in less, and I included the symbols, right? Greater than, now we're talking about a mean to start with, all right? So let's write this down here. I'll erase some of this because it's moved now. Their mean is part of a range here, a spectrum. So their mean has to be greater than or equal to 80. And simultaneously, their mean has to be not equal to 90, but less than 90. This is a situation where you have two conditions referring to the same thing that you could double up, so you can make it an AND type of problem, right? Well, let's do it this way, which might be a little bit more intuitive. If this is the common feature that unites them, we're talking about a mean here. Then let's put mean in the middle. And let's put the inequality symbols and the numbers that are the boundaries around that word. So this one is pretty straightforward, right? Forward, right? You see, this is less than, right? So the mean has to be less than 90 on the high end. And it has to be greater than or equal to 80. The point is facing the 80. So I'm going to keep the open end facing the word mean, just as it is here in the original conditions. Then there is also an equal sign here, so I'm going to put an equal sign. And then the number 80 here. Right? Now, what we can do is we can expand upon this phrase mean to be a little bit less verbal and a little bit more mathy, for lack of a better phrase. Right? I'm going to read this sentence again. Right? If their test scores were 98, 76, 86, and 92, what would be the range of possible scores on a hypothetical fifth test to qualify for a B? The mean is derived, there's a little thought balloon here, from doing what? A sum, which is adding, and then dividing by how many there are, how many tests there are, the number of numbers, if you will. So the best way to symbolize that, adding and then dividing, is to put a line like this, right? And we're talking about 5 tests, right? So I'm going to put a 5 under it, and then write the individual scores that would be added together. I'm going to just put question marks for the moment. Right? You would add everything first to simplify the top, and then you would divide by 5. Right? Could you put the colon with the line through it instead of having it arranged like this? Yes, but what you would have to do in a situation like that is encapsulate what is being added. So you'd have to include a parentheses. All right? You'd have to include parentheses. Anyhow, what I'm going to do is I'm going to move this up here because I need the space to work. Less than or equal to 80 on one side and less than 90 on this side, and figure out what goes in here. All right? Rather than move the slide, I'm going to point to my actual physical copy here. All right, the 4 tests that had occurred are 98, 76, 86, and 95. So that would be first question mark, 98, 76, 86, and 92 rather. All right, and then there's this 5th test. Right, the 5th test should be a variable, right? So you could make it a t, all right, or you can make it an x or whatever you like, right? My instinct is to go with t for test, And sometimes they put a little subscript. It's just a label. Right? If that is T1, T2, T3, T4, that in theory would be T subscript 5. You don't have to put that, you could just put T if you like. Right? Anyhow, let us simplify what we can. Right? If you added all of these together at least, what would you get as a figure? You should get 352. So this would be 352 plus this hypothetical fifth test over the number 5, because that's how you calculate a mean, you divide by 5. Except that we need to calculate what the fifth test would have to be. So I'm going to erase this now because I have sufficiently narrowed it down, right? Alright, now, being this is a spectrum, right? It is an AND type of problem. And I'm going to write 1/2 of it over here. 352 plus t over 5 is, in this orientation, less than or equal to 80, so it would be greater than or equal to 80. The point is facing the 80, the point was facing the 80. And then over here, the same balance here, 352 plus t is less than 90 over 5. My blue is dying. Don't die, blue. Alright. That sounds like a sad Nickelodeon phrase. Alright. Anyhow. Again, because of the nature of this top being the way it is, I can't really reduce these two things to one figure because there's a variable that makes this not like terms. What I can do to simplify is really to perform algebra at this point. So I'm going to move 5 from this side to the opposite side here. Right? And in doing that, I will perform the opposite operation of division by 5 by multiplying by 5, which causes a cancellation effect here. And then to make it legal, I'm going to multiply here. All right? That leaves me with 352 plus t is greater than or equal to 5 times 8 is 40, and then there's this extra 0, so it's 400. Right? And then I'm going to move 352 from here to here. Right? If this is a positive 352 and nobody has ever gotten a negative test score, right? Then to justify moving it, I would have to subtract. So I'm going to minus 352 here and minus 352 here. These cancel. This t is left over. That's the fifth test. And it would be greater than or equal to the difference of 400 and 352, which should be 48. Right? Let me just verify. If you're subtracting this brute force, that's a 10, this would end up being a 9, and this would end up being a 3. That's 8, and that's 4, and that's 0. So yes, that's one end of the spectrum. And then a similar effect happens over here. You would move the 5. That's too faint. Right. Move the 5. For the same reason, opposite operations, opposite of division is multiplying. This is technically above the line, and this is below it, so that's why there's a cancellation effect. Right? That leaves you with 352 plus t to the fifth, t subscript 5, is less than 9 times 5 is 45 with an extra 0. Continuing on here, subtract 352, subtract 352. This cancels. The fifth test is, let's see, less than, the difference should be what? If that is a 10, that becomes a 4 temporarily. This is an 8 here. And that's a 14, and that becomes a 3. 14 minus 5 is 98. All right. So you have that. All right. Now, because this came from something that was doubled up to begin with, it might be practical in this particular example to put them back together that way. So this, we just solved for this fifth test, all right? And we have incorporated the conditions that have to be met. That is, that there were four tests that existed already, and we're trying to figure out, well, what's going to qualify for a B, all right? on this hypothetical fifth test, right? This hypothetical fifth test is in the spectrum of being greater than or equal to 48. A person may not be proud, they may not hang this on the refrigerator, right? But that is the minimum that they would need to get a B overall, right? Point facing the 48, point still facing 48. On the high end, they could get, if they just want to be and nothing better, they would get something less than 98. If they got a 98.5, if they got a 98.1, if they got a 99, they would be beyond the spectrum of B, right? Which isn't bad, it's something to be ashamed of, right? But this is the spectrum, right? They only need for this fifth test to minimally get a 48 or better, right? So on a graph, how would that look? Right. 0 would technically be over here because we're dealing with positives exclusively. 48 would be the first thing that shows up, right? And 98 would be somewhere after it, right? Now, just not to get distracted with the gobbledygook here, let me just erase this.
Yes.
And I'll put this in blue. The spectrum is including 48 is a possibility. It's a minimum, really. All right, and excluding, not including, just using it as a reference end boundary over here. And it would be in between these. So here's our molecule, right? You could get a 48, right? And you can get up to, but not including a 98, right? This spectrum would calculate a B average, right? If this fifth test is somewhere in here, right? So that's kind of cool, right? I think so. I would want a person actually to do better than 48, but I wouldn't be ashamed of it either because your average is a B, right? That's respectable. Okay, all right. Let me turn the light on just for a moment and turn this off and get this curtain back. All right. So we're done with section 6.5. All right, for homework and theory. All right, you want to do section 6.5 in MyLab. I had a good question sent to me the other day. I always post all of this information in MyLab. Sometimes because I have to sort of cut and paste a lot, I'll post it and then come back a moment later and then paste the alteration that I need to. Anyhow, if you get an email that it was missing the link to where the photocopies, the PDF files would be, just go to the page, right, that is our Canvas page, and click on pages and you'll see that chapter 6 is there. All right, I'm sorry, I don't know why it emails you. You should just be able to go look, at, the announcement and it's updated, but apparently it doesn't do that. All right, so that's silly. All right. Anyhow, thank you for sticking with me. We are off on Monday, technically. Here's the calendar. All right, we just covered section 6.5. Monday is President's Day, so you technically have off. I'm looking at the material, section 6.6 and 6.7. It's kind of involved, so what I think I'm probably going to do is I'm going to record something on Monday. You don't have to look at it, all right? You can go about your business, of course. But just not to have it as like a 3 or 4 hour video. It's pretty bad, all right? So I'm still kind of on the fence about that, but you are technically off, right? So you don't have to really do anything on President's Day. All right. Okay. So hopefully you will have a restful weekend with your snookums or whoever you have. All right. I'm envious, really. Because the 14th is just before that, Valentine's Day, right? In the United States, we celebrate Valentine's Day. All right. Anyway, be careful out there. All right. Have a nice weekend.